Hello and welcome to Compassion. This is my third lecture in IR spectroscopy. In this particular video, I will be explaining you about IR absorption frequencies of carbonyl compounds and what are the different factors which affects these carbonyl stretching frequencies. So first of all, what are these carbonyl compounds? Whenever we talk about carbonyl compounds, that means we have got carbonyl group present in the molecule, which is C double bond O. So all the functional groups which consist of these carbonyl group, that is C double bond O, belongs to carbonyl compounds like aldehydes, ketones, acids, esters, amides, acid chlorides and anhydrides. The stretching frequencies of these carbonyl compounds ranges between 1850 centimeter inverse to 1650 centimeter inverse, and this particular variation in these carbonyl stretching frequency is due to large change in dipole moment. So if we see amide functional group, its absorption frequency is the lowest, which is 1675 centimeter inverse, and for anhydride the value is highest, which is 1810 centimeter inverse. And in between we have carboxylic acids, ketones, aldehydes, esters and acid chloride absorption frequencies. So what are the different factors which affects these absorption frequencies of carbonyl compounds? So the factors are electron withdrawing effects, that is minus I inductive effect, resonance effect. These two effects generally operate in opposite ways to influence carbonyl stretching frequency. And then we have hydrogen bonding and one more alpha substitution effects. So first factor which influence carbonyl stretching frequency is conjugation effects. This I have explained in my previous video also. When a carbonyl group is in conjugation with carbon-carbon double bond, then it results in delocalization of the pi electrons. So as the conjugation increases due to delocalization of pi electrons, there is increase in single bond character of carbonyl group, and this lowers the force constant, resulting in lowering of absorption frequency of carbonyl group as well as double bond absorption frequency. So when we compare between alpha beta unsaturated ketone, so for a simple ketone the absorption frequency, so if I have a simple ketone without any conjugation, then the absorption frequency is 1715 centimeter inverse. And when we introduce some conjugation in it, like carbon-carbon double bond, then the value decreases to 1690 centimeter inverse due to increase in single bond character. If we have any aromatic ring like benzene ring as a part of conjugation, so due to increased conjugation, the value declines to 1700 centimeter inverse. So for benzaldehyde, the carbonyl frequency is 1700 centimeter inverse. Similarly, if I consider carboxylic acid like benzoic acid, so for now normal compound containing carbonyl group or carboxylic acid, the carbonyl stretching frequency is 1710. But when we introduce an aromatic ring to it, which gets involved in conjugation, then the value decreases to 1680 centimeter inverse. So as the conjugation increases, single bond character increases and hence absorption frequency decreases. Second factor is ring size effect. Six-membered rings are highly unstrained, or we can say strainless ring. There is no strain present in six-membered ring. If ring size is lesser than 6, then there is increased angle strain. So decreasing the ring size increases the absorption frequency of carbonyl group with increased angle strain. So let's see, if as I said, when we have a ketone, simple aliphatic ketone, the value is 1715 centimeter inverse. But when that ketone becomes a part of a ring like cyclopentanone, then the value increases to 1745 centimeter inverse. If we compare the ring size. So cyclopentanone is larger ring as compared to cyclobutanone. In case of cyclobutanone, there is increased angle strain, and as the angle strain increases, the absorption frequency will also increase. So, on comparing with cyclopentanone, cyclobutanone has higher absorption frequency of carbonyl group, which is 1780 centimeter inverse, while for cyclic ketone it is 17, for cyclopentanone it is 1745 centimeter inverse. Similarly, if we have an ester, then the carbonyl stretching frequency for ester is generally 1735 centimeter inverse. And when that ester is part of a ring, which is commonly called as lactone, then the value of carbonyl stretching frequency increases to 1770 centimeter inverse. Same is the case with cyclic amides or lactam also. If we have aliphatic amide, then carbonyl stretching frequency is 1690 centimeter inverse, and when this carbonyl group cyclic amide becomes part of the ring, then the value increases to 1705 centimeter inverse. So here we can say that as the ring size decreases, angle strain increases, and hence the absorption frequency value also increases. Next factor is alpha substitution effects. So whenever we have a carbonyl group, the adjacent carbon is the alpha carbon atom. And if on that alpha carbon atom some halogen like chlorine, bromine or any other halogen is attached, then there will be electron withdrawing effect. So due to that electron withdrawing effect of halogen, the electron density will pulled towards halogen, thereby shortening of carbon oxygen double bond takes place or tightening of pi bond takes place. As this carbonyl double bond shortens, there is increase in the force constant, and when the force constant increases, that means bond has become stronger, so absorption frequency will also increases. So when any alpha substituent is present, then there will be increase in the absorption frequency. Next factor is hydrogen bonding. So hydrogen bonding to a carbonyl group lengthens carbon oxygen double bond, and hence there is lowering of force constant resulting in lowering of absorption frequency. So if we consider a carboxylic acid dimer, then there will be decrease in carbonyl stretching frequency. Here I have shown example of methyl salicylate, where we have an ester and hydroxyl group at ortho position with respect to each other, and there is intramolecular hydrogen bonding. Due to this intramolecular hydrogen bonding, the carbon oxygen double bond here stretches, and there is lowering of the force constant, and hence methyl salicylate shows carbonyl stretching frequency at a value which is lower than 1700. Generally it is 1680 centimeter inverse. So let's see different carbonyl groups, functional groups, one by one. If we consider aldehyde, so for simple aliphatic aldehyde, the carbonyl stretching appears in the range of 1740 to 1725 centimeter inverse. Whenever we get band in at around 1700 centimeter inverse, it is 100% carbonyl group. Then we need to check whether it is aldehyde, ketone or any other functional group. As I said that as the conjugation increases, the carbonyl stretching frequency decreases due to increase in single bond character. So here we can see we have alpha beta unsaturated aldehyde. So when we compare with simple aldehyde, the carbonyl stretching frequency for alpha beta unsaturated aldehyde is in the range of 1700 to 1680 centimeter inverse. And if we have aromatic aldehyde, then the value is 1700 to 1660 centimeter inverse. Next functional group is ketone functional group. When we compare carbonyl stretching frequency for a ketone with an aldehyde, then aldehyde is generally having higher carbonyl stretching frequency value as compared with ketone. The reason is that in case of ketones, we have two alkyl groups, and alkyl groups are electron donating group. Since here both the alkyl groups are donating the electrons towards this carbon or carbonyl bond, so there is decrease in the force constant and hence the value also decreases. In case of aldehyde, we have only one alkyl group, so the electron donating effect is lesser, and that is the reason the value for aldehyde is higher. So as I said that for ketones, the carbonyl stretching frequency appears in the range of 1720 to 1708 centimeter inverse if it is aliphatic ketone. When we introduce some conjugation like alpha beta unsaturated ketone, the value declines to 1700 to 1675 centimeter inverse. And if we have an aromatic ketone, that means we have some benzene ring in the molecule, then the value decreases to 1700 to 1680 centimeter inverse. And we have two aromatic groups, then the value will decline further because there is conjugation with two aromatic rings. So the range is 1670 to 1600 centimeter inverse. If ketone is a cyclic ketone, then the frequency increases with decrease in ring size. So let's see a few examples of ketones. So here we can see that in this we have one aromatic ring, say it is benzene ring, and one alkyl group. So here we have conjugation as well as electron donating effect of alkyl group. So the range is 1685 centimeter inverse. For alpha beta unsaturated ketone, it is 1680 centimeter inverse because there is less conjugation. And when there are two aromatic rings, then both the rings are involved in conjugation. So value is 1665 centimeter inverse. So this is the conjugation effect. When, as I said that ring size also affects the carbonyl frequency. So as the ring size increases, the absorption frequency decreases. So here we can see that when we have cyclopropanone, then the value is highest, which is 15 centimeter inverse. And for cycloheptanone, it is 1705 centimeter inverse. The reason is as the ring size increases, the angle strain decreases. So when there is higher angle strain in the molecule, then the value will be higher. So for cyclopropane, it is 15 centimeter inverse. For cyclobutanone, because the ring strain is lesser as compared to cyclopropane ring, so the value is lower, 1780 centimeter inverse. For cyclopentanone, it is 1745 centimeter inverse. As I said that 6-membered rings are strainless ring. So when we compare cyclohexanone with some aliphatic ketone, then both of them are not having any strain. So their value is similar, which is 1715 centimeter inverse. Next functional group is carboxylic acid. If we want to identify carboxylic acid, then we need to see two absorption frequency. One in H stretch region, which is in the range of 3600 to 3000 centimeter inverse, and one in carbonyl, that is double bond region, which is around 1700 centimeter inverse. If both of these shows absorption bands, that means carboxylic acid is present in the molecule. So for OH, I have already discussed in my previous video. Right now we are talking only about carbonyl group of carboxylic acid. So carboxylic acid generally it exists in monomeric form if the solution is very dilute. So in dilute solution, we will get carbonyl stretching frequency, which is very broad band uh, in the range of 1730 to 1700 centimeter inverse. We get carbon oxygen single bond stretching vibration, which is a medium band between 1320 to 1210 centimeter inverse. And as I said that in H stretch region, we will get very broad band for hydroxyl group, which is in the range of 3400 to 2400 centimeter inverse. So when this OH, broadband and carbonyl both are present, that means we have carboxylic acid. So this is for a dilute solution where there is no hydrogen bonding. So in that case, there will be electron withdrawing effect of this OH group. OH is going to pull the electron density towards itself. So the value for carbonyl will be around 1760 centimeter inverse. If acid is we take concentrated solution, then acid generally dimerize via hydrogen bonding. This is intermolecular hydrogen bonding. Dimerization generally weakens the carbonyl stretching frequency and hence lowers the force constant. So there will be lowering of carbonyl group, which is 1710 centimeter inverse as compared to diluted solution. So dilute solution of carboxylic acid shows higher carbonyl stretching frequency as compared to concentrated solution. Next functional group is ester functional group. In ester functional group, there is electron withdrawing effect of OR group. Due to this electron withdrawing effect, the carbon-oxygen double bond strengthens and hence force constant increases, resulting in increase in absorption frequency value. So for ester, always remember that absorption frequency is around 1735 centimeter inverse. But if we compare with methyl salicylate, where we have ester group and OH group is also present, but there is intramolecular hydrogen bonding. And due to intramolecular hydrogen bonding, this carbon-oxygen double bond frequency is going to shift towards lower value, which is 1680 centimeter inverse. Sorry, here by mistake I have shown this OH value. For ester we don't get OH because we don't have OH functional group. So let's see how the value for ester changes. So for aliphatic esters, the carbonyl stretch appears in the range of 1750 to 1735 centimeter inverse. As we introduce conjugation, that is carbon-carbon double bond, then uh, we get the value which is lower than normal aliphatic esters, which is 1740 to 1715 centimeter inverse for carbonyl. Apart from that, we get carbon-carbon double bond frequency between 1640 to 1625 centimeter inverse. If ester group is present on some aromatic ring, then there is conjugation of this carbonyl group with aromatic ring like phenyl ring. So the value will decrease to 1740 to 1715 centimeter inverse. If we have this kind of ester where you can see we have olefinic double bond but there is no conjugation. So here what happens, conjugation of single bonded oxygen atom is with carbon-carbon double bond. Okay, this carbonyl carbon oxygen double bond is not in conjugation with carbon-carbon double bond, while carbon oxygen single bond oxygen atom is in conjugation. So the value will be higher, which is 1765 to 1762 centimeter inverse. If ester is part of a ring, that is lactones, then carbonyl frequency increases with decrease in ring size as the angle strain increases. So here we can see is ethyl butyrate. There is no conjugation and it is normal aliphatic ester. So carbonyl stretching frequency for ethyl butyrate is 1738 centimeter inverse. If we introduce a conjugation, you can see alpha beta unsaturated ester, that is methyl methacrylate. So due to conjugation, the value decreases to 1725 centimeter inverse. And when we introduce conjugation, but we have aromatic ring like methyl benzoate, then the value is 1724 centimeter inverse. In case of ester, we can have conjugation with single bonded oxygen atom also, because oxygen contains lone pair of electrons. So when we move these electron pair, so there is charge separation. We have positive charge on oxygen and CH2 minus. So in that case, the value is going to decline. So as I said, for ethyl butyrate, it is 1738 centimeter inverse. For vinyl acetate, because single bonded oxygen is in conjugation, so the value is higher, which is 1662 centimeter inverse. And for phenyl acetate, the value is still higher, which is 1665 centimeter inverse. So when the conjugation of ester is with single bonded oxygen atom, then the value increases. As I explained earlier, that if there is intramolecular hydrogen bonding, then the carbonyl stretching frequency declines. So for example, methyl acetate, salicylate, whose value is 1680 centimeter inverse. So here you can remember that for a normal ester, the value is in the range of 1738 centimeter inverse. And if uh, the carbonyl group of ester is in conjugation with single bonded oxygen atom, then the value will be greater than 1738 centimeter inverse, in the range of 1765 centimeter inverse, because it is in conjugation with oxygen atom. If we have alpha beta unsaturated ester or aryl conjugation is present, then the value is going to decline. That means it will be lesser than 1738 centimeter inverse. It is in the range of 1725 centimeter inverse. So this is very important thing in ester functional group. If we have cyclic ester, then we need to understand ring size effect. So as the ring size decreases, angle strain increases, and hence the vibrational stretching frequency will also increase. So here we can see that for six-membered cyclic ester, the value is 1735 centimeter inverse. For five-membered, the value is 1770, and for four-membered, it is 1820. So as the ring size is decreasing, angle strain is increasing, and hence absorption frequency is also increasing for carbonyl group. If we have alpha beta unsaturation in cyclic esters, so as the conjugation increases, then the value is going to decline as compared between these two six-membered. One is without any conjugation, and the other is alpha beta unsaturation, conjugation is present, so the value is lesser. Similarly, if I consider this without conjugation, the value is 1770, but when we introduce alpha beta conjugation, the value declines to 1750 centimeter inverse. If we have conjugation with oxygen atom, then as I explained you previously, the carbonyl stretching frequency is going to increase to say 1760 centimeter inverse. As we can see here, for five-membered without conjugation, it is 1770. And when there is conjugation with oxygen atom, then the value is very high, around 1800 centimeter inverse. Next functional group is amide functional group. If we talk about amide functional group, that means we have CO and H2, or we can have primary or secondary amines. So we need to look out for two bands, one in the double bond region for carbonyl group around 1700 centimeter inverse, and other is in H stretch region for amines group. If both of these are present, that means amide functional group is present in the molecule. So when we are talking about amide functional group, it is having lower frequency value for carbonyl, which is 1690 centimeter inverse as compared to any other carbonyl compound. Here the lone pair of electron present on nitrogen atom uh, is in conjugation with the carbonyl group, which leads to increase in single bond character. And due to increase in single bond character, carbonyl absorption frequency declines to 1690 centimeter inverse. Now, when we are talking about amide group, it's not necessary that always we'll have NH2. We can have primary or secondary also. So, for primary group, NH2 group, we get a band in the range of 3050 to 3180 centimeter inverse. For secondary, we get in the range of 3300 centimeter inverse. If we are talking about cyclic amides, then again, as the ring size decreases, angle strain decreases. So, four-membered cyclic amide will have higher value due to increased angle strain as compared to six-membered cyclic amide. Next group is acid chlorides, where we have carbonyl group and chlorine. We can have other halogen as well. So acid chlorides generally show carbonyl stretching frequency in the range of 1810 to 1775 centimeter inverse. This is again due to presence of electron withdrawing effect of halogens. But if any conjugation is present, then the value is going to decline to 1780 to 1760 centimeter inverse. Apart from this, we get a band for carbon halogen single bond between 730 to 550 centimeter inverse. Next is anhydride functional groups. Anhydride contains two carbonyl groups, so we are going to get two absorption bands which are due to symmetric and asymmetric stretching vibrations, and anhydrides generally have higher value between 1830 to 1800 centimeter inverse. First band will appear and second band will appear between 1775 to 1740 centimeter inverse. Like any other molecule in this also, as the conjugation increases, absorption frequency will decrease. As the ring strain increases, absorption frequency will increase. Next is amine functional groups. We can have different types of amines. Like primary amine, we have NH2. Then we have secondary amines and tertiary amines. So if we have primary amines, we get two stretching bands for NH group in the range of 3500 to 3300 centimeter inverse, because we have two NH single bond. If we have secondary amine, since we have only one nitrogen hydrogen bond, we get one band. And for tertiary amine, we don't get any band in uh, stretching NH stretch region, because there is no hydrogen attached to nitrogen atom. Apart from that, we get bending vibration for NH in the range of 1640 to 1560 centimeter inverse, and then out of plane bending at around 800 centimeter inverse, and carbon nitrogen single bond in the range of 1350 to 1000 centimeter inverse. So generally, uh, hydroxyl group and NH group, they show band in the same range, but NH bands are sharper than OH bands. OH bands are generally broader. Next group we have nitrile. So nitrile shows absorption frequency in the range of 2200 or 20 to 50 centimeter inverse. And as the conjugation with double bond or aromatic ring increases, there will be shift towards lower frequency values. If we have nitro compounds, then if aliphatic nitro compound is present, then we get band in the range of 1600 to 1530 centimeter inverse, and symmetric stretching between 1390 to 1300 centimeter inverse. When aromatic nitro compound is present, there is conjugation, so values are going to be lesser as compared to aliphatic nitro compounds. For alkyl halides, like if we have carbon chlorine bond, we get band in the range of 785 to 540 centimeter inverse, and for carbon bromine in the range of 650 to 510 centimeter inverse. So this was all about IR spectroscopy. In my next video, I'm going to begin with NMR spectroscopy. So in these lectures on IR spectroscopy, I have discussed about what are the reason behind decline or increase in absorption frequency values. So instead of mugging up all the values, it's better to understand what is the reason and in what range are we going to get the value. So I hope you like this video. Please like, share and subscribe. And in my next lecture, I'll start with NMR spectroscopy. Thank you so much.